All right, welcome Chem 2341. We're continuing on with Chapter 6, Part 4, SN1 Reactions. Okay, in the last set we showed you what SN2 reactions are. In this set we'll show you what SN1 reactions are. Okay, just like the name suggests, it's going to be a nucleophilic substitution, but it's going to be unimolecular, which means that we're going to have the carbon halide bond break first. And when the carbon halide breaks first, the halide takes both of the electrons from the sigma bond, giving you a carbocation. And then that carbocation can wait around and react with the nucleophile. So again, the S is substitution, the N is nucleophilic, and 1 means unimolecular. So the first step is the slow step. That's the breaking of the carbon halide bond to create the carbocation. Now the carbocation will convert into an sp2 hybridized planar structure and have the empty p orbital above and below the plane. Okay? So the next step that happens is what we call the fast step. Any nucleophile or any lone pair can now react with that carbocation to create a new bond. And in this case, we create a charged intermediate. Then any base can come along and deprotonate that charged intermediate to give us our neutral intermediate. Both the attack by the nucleophile and the deprotonation step are fast steps. Therefore, the only thing that determines the rate of the reaction is actually the concentration of the alkyl halide, since the alkyl halide has to break all by itself first before anything else happens. Okay? So as such, because the SN1 is only affected by the idea of the carbocation, we have to think about the stability of the carbocation as why we're going to do it. So in contrast, in the exact opposite of SN2 type reactions, the methyl group reacts slowest, the primary halide is next, tertiary halide is the fastest of the set. Okay? So that means that our tertiary halides undergo SN1 very rapidly. Our tertiary alkyl halides go very rapidly, our secondaries go more slowly, and our methyls and our alkyls tend to not undergo SN1 reaction. But why? It goes to the stability of the intermediate. So in our SN2 type reaction, we only have a transition state and then it's going to products. In the case of our SN1 reaction, we'll actually end up with two humps. Our first transition state is the elongation of the bond between the carbon and the halide, and that creates our first transition state. When that bond breaks, we have our intermediate step. Our intermediate is this carbocation. The carbocation is isoluble and is an actual, interactive species in the system. Now, as the nucleophile comes in and starts to form a bond with that carbocation, that's our second activation energy and our second transition state. And then as those two form that sigma bond, it decreases in energy to our final products. Okay? So being that we have to form this carbocation, that means the more stable the carbocation, the more stable the transition state. And the more stable the transition state, the lower the activation energy of the fast step. Okay, so let's talk about carbocation stability. Carbocations are classified by the number of R groups attached to the carbon we're concerned with. Okay, so just like in the case of alkyl halides, if you only have one carbon bonded to the carbon you're looking at and that the halide's on, we call that a primary halide. So in this case, we have a methyl cation, which has no carbon bonded to it, the primary carbocation, which has one carbon bonded to it, secondary, 2 carbons bonded to it, and tertiary has 3 carbons bonded. Now, the tertiary carbocation is the most stable, followed by secondary, primary, and methyl. Okay. So, why are these carbocations more stable in tertiary and secondary than in the primary and methyl? It has everything to do with the inductive effect and hyperconjugation effects of those carbons bonded to the carbon with the positive charge. So let's look at that inductive effect. Now, remember, we talked about this when we did acidity of carboxylic acids and other things. Okay? Electron donation or withdrawing through a sigma bond causes an electronegativity difference between the different atoms. Okay? Alkyl groups are technically electron donating by induction because it's a very non-polarized bond. It can inductively donate some electron density through the sigma bonds to the carbon that has the positive charge. Okay? Alkyl groups are more polarizable than the hydrogen atom and therefore can donate more electron density. Okay? So in general, the more alkyl groups you have added to a carbon with a positive charge, the more stable the cation can be because of the 3 donations through sigma bonds is more stable than 2 donations through sigma bonds, which is more stable than 1 donation through a sigma bond, which is of course more stable than the methyl cation. Okay, now hyperconjugation also plays a role here in the fact that you have the sigma bond between the carbon and the hydrogen, and although each of those bonds is sp3 hybridized, they can still partially overlap with that empty p orbital on the sp2 hybridized carbocation carbon. So what we can see here is there's a little bit of pi overlap between the sp3 hybridized orbital and the empty p orbital. And when you have a tri-substituted cation here, you have that hyperconjugation through 3 different bonds possible. And if you look at that methyl cation there is no possibility of hyperconjugation because there's no sp3 hybridized orbital allowed to overlap with it. Okay? And so by looking at the number of different bonds available to do the hyperconjugation, the more hyperconjugation available, the more stable it is. Therefore, tertiaries are always more stable than secondaries, because if you look at that tertiary, it has 9 bonds possible for hyperconjugation. The isopropyl only has 6 bonds for hyperconjugation. The ethyl only has 3 bonds for hyperconjugation, etc. Now, what's also possible when we have a carbocation is that the carbocation will want to create the most stable carbocation possible. So what that means is we have the possibility of transferring a hydrogen from one carbon to another to create a more stable carbocation. Okay? So if we start with a secondary carbocation and it's possible to move a hydrogen over one carbon to make it into a tertiary carbocation, it will. So let's look at that top reaction here. Okay, we have a bromine on a secondary carbon in the 2-bromomethylbutane. And if we go along the upper arrows here, we can, through an SN1 mechanism, we would, of course, break that carbon-bromine bond first. When we break that bromine-carbon bond, the bromine takes the electrons, leaving the carbon as a positive charge. What can now happen is it has a hydrogen on one carbon over that would allow it to transfer over, and it's called a hydride shift because both electrons from that sigma bond with that hydrogen are moving over with it to give us a tertiary carbocation. Once we have that tertiary carbocation, it can then react with poor nucleophiles like water to then generate our final product. Okay. If we had a reaction where instead of using water, we actually had a stronger nucleophile like hydroxide, we could actually undergo an SN2 type reaction because of the stronger nucleophilicity of the hydroxide, and we would end up with the bond to the secondary carbon. So by SN2, we create the secondary alcohol. By the SN1, we create the tertiary alcohol. Okay. Note, it will only transfer one carbon and only to make a more stable carbocation. Okay, so we can do this with hydrogen, but we can also do it with a methyl group. The methyl group is still available to us to actually do that same shift. Both electrons from that carbon-carbon bond will transfer over to one carbon to give us the more stable carbocation. So if we look at the top reaction here, the first step in our SN1 reaction is to remove bromine, creating a carbocation. In this case, our carbocation is a secondary carbocation. Okay. It has 3 methyl groups adjacent to it. If it transfers one of those 3 methyl groups over to that secondary carbocation, it creates a tertiary carbocation. Once we've created that tertiary carbocation, it will then react with any nucleophile, even a poor nucleophile like water, to create our protonated species, and then by using water as a base, we'll get to our neutral species. Note, just like in the hydride, it only transfers over 1 carbon, and it will only transfer to create a more stable carbocation. Okay, so to reiterate that, once you form that secondary carbocation, it will only shift over to make a tertiary carbocation, and it'll only shift 1 carbon over, not anymore. So if we look at the first reaction here, we have a secondary carbocation here at the top, and we have the possibility of doing a hydride shift. However, if we go to the left side here, we do a 1,2 hydride shift, it'll only give us a secondary carbocation. Therefore, there is no reason to do that reaction, and therefore it does not transfer over. Now, let's look over at the other side, on the left side here. If we do transfer, we can actually get a tertiary carbon, but it's 2 carbons over. That would be a 1,3 hydride shift. It will not transfer over to that 3rd carbon, and therefore that reaction does not happen either. So we always form the more stable carbocation, and we only do a 1,2 hydride or a 1,2 methyl shift. Okay, how can this help us? Well, this can help us a lot if we have ring systems, especially if we have 3, 4, and 5 membered rings. By doing that transfer and expanding the ring to make it bigger, it actually relieves ring strain. So in the case of our material at the top left here, we can undergo an SN1 first step to create our carbocation and have our bromide leave as the anion. Okay. Now in this case, we're doing a 1,2 methyl shift within the ring to move over to not only create a now 6-membered ring, but to create a tertiary carbocation. So we went from a secondary carbocation to a tertiary carbocation and expanded the ring to relieve any ring strain. Okay, so it'll only happen to relieve ring strain in 2 and 3 membered rings. It'll expand 5 and 6 membered rings if you're increasing carbocation stability, but only if you're increasing carbocation stability. Okay, so because we've actually changed our hybridization from an sp3 hybridized carbon, which is tetrahedral, to an sp2 hybridized carbon, which is trigonal planar, we now have a difference in the way the nucleophile can come in and attack. Okay? So now that we've formed this planar structure, the nucleophile can come in and attack that empty p orbital at either the top or the bottom of that. Therefore, there's no specificity on whether it's going to come in from either side. And therefore, you're going to get half of the attacks from one side and half of the attacks from the other side. What that means is that if you started with a chiral compound and you went through that carbocation intermediate, which is planar, you're going to have half of it come to the same side as where the bromide was, but half of it's going to come to the back side. So what that means is that we're going to end up making a mixture of the 2 enantiomers, or making a racemic mixture. Okay? Unlike SN2, where you get inversion of the stereocenter, we now get a racemization of that stereocenter.